Hello and welcome back. In this session, we're going to talk about identity elements of the basic set binary operations, the union and intersection. And we'll see that just like in Boolean algebra, we can redefine these operations as set multiplication and addition. So we'll talk about the set multiplicative and additive identity elements. We'll start with the concept of disjoint sets, just so we can use this term later on. It's a very simple concept. Two sets that have no elements in common are called disjoint. And since the intersection of sets is the set of common elements, this set must be the empty set for two sets that are disjoint. So if sets x and y are disjoint, that implies that the intersection of sets x and y equals the empty set. Now, we had defined in Boolean algebra multiplication and addition as the and or operations respectively. And we saw that in the case of multiplication of Booleans, this was very similar, in fact identical to multiplication of natural numbers, as long as we restricted ourselves to the numbers 0 and 1. So we can do the same thing with sets. We can assign the union operation, or we can define the union operation as set addition, and we can define the intersection operation as set multiplication. We already have a way of doing set multiplication, and that's the set Cartesian product. This is a new way of defining a product of two sets where the operands of the multiplication operation are sets. It doesn't take away from the Cartesian product, it's just another way to do a product. The default product, if you do see a set product, is going to be the AND operation. Now let's look at a little bit more in detail. The intersection is a little bit less intuitive than the AND operation in logicals was. So in logicals we had the 0 and 1 resulting in common truth. If we had a 1 on both sides of the multiplication operation, we end up with a true or 1 result. So we were looking for common truth, or a common 1. A 0 on either side results in a 0 or false of Boolean multiplication operation. In sets, we're really doing the same thing. We're looking for common elements this time. Now, unfortunately, we cannot write it directly equivalently to the multiplication operation of natural numbers. But we are doing something very similar. We're looking for common elements, whereas in logicals we looked for a common 1. We are now looking for any common elements, and we will call that the set product by default. Now that we have defined set addition and multiplication as the union and intersection, let's look at identity elements for these operations. So let's look at the additive identity element, or the union identity element. So remember, for an element to be an identity element of an operation, we must have that for all elements x in our domain, x operation question mark, where question mark is our identity element, equals x. So x union question mark must equal x. So we must find an element where the union with any set results back in that set. Now we know that the union operation is idempotent, so we could take x itself, x union x equals x, but that same x will not hold true necessarily for another set. So is there an element for which this is always true for any set? And it turns out that the empty set fits the bill here. So x union empty set is going to equal x again. no matter what x is. We can do a union with a set that has 0 elements in it, and we get the same set back. So the empty set is the additive identity element under the union operation or set addition. In Boolean algebra, we saw a multiplicative identity as the one element because x and 1 equals x for all x in the Boolean domain, or x times 1 using the definition of Boolean multiplication as the AND operation. Can we do something similar for the set intersection? Can we have an element question mark where x intersection question mark is going to return x? It turns out that yes, we can. Remember, the intersection results in a set of common elements. So if our question mark element of our power set contains all possible elements that are available in the domain, then our intersection is always going to equal the smaller set, x in this case. So if our set S contains every possible element, then it's also going to contain whatever is in x. So x intersection, the universal set, is going to return x. And therefore, the universal set of whatever our domain is going to be the multiplicative identity element for the set intersection or set multiplication. Now, what about inverse elements? Let's look at a possible additive inverse for set addition. So remember from the definition of inverse elements, we must have an element question mark where x union question mark equals the additive identity, which is the empty set. So we must have an element question mark where x union question mark returns the empty set. In other words, we must do a union with something that wipes out the set x. In real numbers, we had the negative of a number, where if we added that to our original number x, it would wipe out that number and return the 0 element, which was our real number additive inverse element. But how do we get an empty set with a union? The union can only have two possible effects. If we do a union with a set that contains the same elements, we get or fewer, then we get the same set back. So the set is unchanged. If we do a union with a set that has more elements or different elements from our original set, then we get a larger set than we had. So the result is always either the same set or a larger set is returned by the union operation. So there is no such element. There is no element that reduces the number of elements in a set under the union operation. So we'd have to define addition in a different way. We define set addition as the union operation. There is no inverse element for that operation. The same is true for the multiplicative inverse. We could ask, is there an element question mark where x intersection question mark equals our multiplicative identity, which we saw was the universal set. So an intersection of x with something must yield the universal set. We also find that there is no such element, because we're not going to get a set larger than x with an intersection operation. So we do not have inverses for the definitions we have for set addition and multiplication. So let's summarize real quick what did we cover here. We defined set addition as the union and set multiplication as an alternative to the Cartesian product. We saw another way to do set multiplication as the intersection operation of sets. We saw identity elements, the empty set and universal set for those operations respectively. And we also saw that there were no inverse elements under these operations. We cannot get a set smaller, and smaller meaning of lower cardinality, than the set X with the union operation. And we cannot get a set larger than X, so we cannot move toward the universal set with any intersection of any other set. So that means we did not have inverses for set addition and multiplication as defined by the union and intersection operations. We also defined the term disjoint sets.